Hi, this is Greg Monty. This is the CERT Education Series covering the modules called Light and Waves. Let's get started. We're going to talk about light waves and sound waves both. Light waves transmit energy and not matter. Remember that. Waves do not transmit matter. Waves are moving energy and travel from a source when a vibration is created. You can see some vibrations on the right-hand side there. These vibrations are carried as waves and transmit energy. Light waves are unique because they can travel through a vacuum like space. That's how we see starlight, for instance. No matter what the medium, no specific medium is required to be able to transmit these waves, light waves. Light waves are also called transverse waves, while sound waves are called longitudinal or compression waves. And sound waves cannot travel through a vacuum. So let's look at both transverse waves and longitudinal waves. The characteristic of transverse waves is that the particles move perpendicular to the direction of the wave. In a longitudinal wave, the particles move parallel to the direction of a wave. You might think about a slinky for a longitudinal wave. It compresses and expands as it moves. That's a longitudinal wave. So what are the characteristics of light? First, they don't transmit matter, just energy. And wave behavior can be described in terms of its speed. So waves have properties of wavelengths, troughs, crests, and amplitudes. We'll see those in the next diagram. Here you can see the wavelength on the right, a longer wavelength diagram on top, and a shorter wavelength diagram below. And wavelength, which is typically given as the character lambda, is the distance between any two corresponding points on a wave, measured in meters. And frequency is proportional to the wavelength, is inversely proportional to the wavelength, and it's measured in hertz, which is cycles per second, and the symbol Hz. And last, there's a relationship between frequency and wavelength, and it's given as F frequency equals C over lambda, or wavelength. So C is the wave speed. If you were talking about the speed of light, C would be 3 times 10 to the 8th meters per second. But C can also be a sound wave, which is much slower than the speed of light. So wave properties, we know they have crests and troughs. The crest is the top of the wave, where the displacement is the highest away from the equilibrium, and it's the maximum point. And the trough is the opposite of a crest, where the displacement is the lowest or the minimum point of the wave. An amplitude is a measure of the maximum displacement from the equilibrium line. So from equilibrium to crest or equilibrium to trough, that represents the amplitude of the wave. So we're going to do 5 experiments today in this particular module, and we'll start with just making a simple wave on your desk or table. The method is that the students will be paired up and given a piece of string by the teacher. That string has a ring on one end and just open string on the other. And one student is going to hold the metal ring on top of the desk, while the second student moves the string back and forth, faster, slower, bigger, or smaller, and creates some transverse waves. And you'll be able to see that the string is just going up and down and up and down, but the wave moves back and forth along the length of the string. So what are the results? Write your observations about the waves while your teacher collects all the strings from the class and delivers a light meter to your station for experiment number 2. So let's move on to light intensity and how we measure light intensity. Light intensity is measured in lumens, And 1 lumen is equal to the total quantity of visible light from 1 candle. And a light meter will be used in experiment 2. The unit of measurement for the light meter is given in lux. And 1 lux is equal to 1 lumen per meter squared. And this will be a little bit more clear in the image on the next slide. So 1 lux is 1 lumen per meter squared. And here we see sort of the comparison between lumens, foot candles, and lux. The lumen is the light from 1 candle, and you can see that here. And there's 2 different measures of that light intensity. If you place that candle 1 foot away from a 1 foot square and measure the light that strikes that square, then that's 1 foot candle. Similarly, 1 lux is the metric version of that. 1 candle 1 meter away from plane, measure the light that strikes that 1 meter by 1 meter plane, and that represents 1 lux, or 1 lumen per meter squared. Experiment 2 is going to be doing some light exploration using your light meters, which have been passed out to you. So the first thing I'd like you to do is turn on the meter. That's the green switch. And then set the meter to 2000, which is the lowest setting of the 3. And then use the light meter with the cover off to measure lux in 5 different places in your classroom or out in the hallway, someplace close to your classroom. Note that the meter cannot measure direct sunlight, and you'll see that when you do one of the answers to one of the questions in the lab sheet, the student lab sheet. It'll just saturate the meter, and it won't give a reading because the light is way too bright outdoors. So record what your lux measurements are in your lab sheet. There's enough for 5 measurements. And make note of the types of surroundings for each of your measurements. Surroundings means how close was the meter to the ceiling, to the floor, to the windows. Were the windows covered with shades, and were the shades closed? Was it a sunny day outside, a cloudy day outside? These are the things that could affect the light meter readings. And record your observations and conclusions in your lab sheet. Note, your teacher will collect all but 8 of the light meters, leaving 8 stations out in the classroom, and combine students into groups of 8 for experiment number 3. Let's move on to traveling light. What can happen to light as it travels from a source? So light, first of all, can be reflected. That's light that bounces off an object. Mirrors, glass, and shiny metals or smooth metals will reflect light. What else can happen? It can be refracted. Light can be bent when it passes from one object to another. Here you see a piece of glass or plastic and a block on a table, and you see a straw placed into a glass with water. So refraction is due to the difference in the density of the 2 objects. Higher density materials cause waves to slow down, and the light appears bent. What else can happen? You can have something called absorption. Absorbed light is absorbed by matter, converting the light energy into internal energy, such as heat. You know this when you stand outside in the sun. Your clothes get warmer, especially if they're black. That's because the absorbed light is turned into kinetic energy or heat. A material that either reflects all light or absorbs all light is called opaque. What else can happen? You can have scattered light. As light passes through an imperfect medium that deflects the light from a straight path. A good example is our atmosphere, which is filled with water particles or moisture, and that scatters the sun's light rays to produce the blue color in the atmosphere. And the reason we see blue is that those water particles absorb all the light except the blue, and the blue is reflected, and that's what we see. Sound does, but light does not diffract. This is true only until you get to very, very short distances from that light might be going through a slit or a diffraction grating. So this is really a statement about light with very big openings, like through a doorway. It doesn't diffract around a doorway. So sound waves can bend around an edge or opening in a wall, like long sound waves, long sound wavelengths. And light waves travel in a straight line and do not diffract until the opening for the light to travel through becomes very small, or comparable to the wavelength of light, which is only 300 to 800 nanometers for visible light. Rainbow glasses that you're going to use later in this, in one of the experiments in experiment 4 and 5, have little diffraction gratings in them that are very, very small, on the order of visible light wavelength, and that diffracts the light and causes a white light to turn into a spectrum of visible light because of the diffraction. So let's move on to experiment 3. Let's look at some of the ways light travels. Students are going to be in 8 lab stations with a light meter. The teacher is going to also distribute 8 lamps, possibly with extension cords if they're needed. And the teacher will distribute the following materials in an envelope: aluminum foil, white paper, black paper, and blue cellophane. So what happens to the light as it travels from the source? The lamp is going to be about 12 inches away from the light meter over here on the right, and we first want you to just record the intensity of the light, or the lux, from that lamp when that light meter is about 12 inches away. And next I want you to place a piece of aluminum foil halfway between the light and the light meter, and read the meter and record the data in the data table in the student lab sheet. Then we want you to repeat that same experiment, putting the aluminum foil away and using white paper, then black paper, and then blue cellophane, and between the lamp and the light meter, and record all those readings in your data table in the student lab sheet. Think about reflection, refraction, absorption, and scattering when making your observations. Your teacher will be collecting the light meters, lamps, extension cords, and the envelope of paper and materials while you are completing your lab sheets. Let's move on to the continuous emission spectrum. How do we see the visible spectrum? Well, I've already mentioned that the visible spectrum is approximately 400 nanometers to 700 nanometers. And those are the colors of the rainbow that we see with our eyes. And how is it that we see this information with our eyes? Well, when you look at the way the light works, the object that's being viewed is the color that reflects off of that object. So light strikes the object and it reflects off. So if it's a red object, it'll be a red light that we see. And that's because red is the only part of the visible spectrum that object reflects. Everything else is absorbed and not seen. So the light goes through a couple of lenses, the cornea and the lens, and then that focuses down to a point or a pixel on the back of our retina. So the light rays focus on the retina, and in that retina, in that location inside the eye, are millions of rods and cones. The rods detect the intensity of the light or the brightness, and the cones detect whether it's red, green, or blue, or some other combination of those colors. And then those cones send information to the brain. The brain interprets that as seeing red or blue or green or purple or whatever color in the spectrum it sees. And the pixels in the eye are many. There are 10 million pixels in the human eye, and this picture on the left has about 16 million pixels in it. The term pixel is actually short for picture element, and these small little dots are what makes up the images on computer displays. So let's think about the electromagnetic spectrum. Electromagnetic radiation travels in the form of waves covering a wide range of wavelengths and frequencies. Note the visible range is just a small portion of the big electromagnetic spectrum. And the electromagnetic spectrum covers wavelengths of light from long radio waves to short gamma waves. Here's a representation of that electromagnetic spectrum. On the left-hand side, you see short wavelengths, and on the right-hand side, much longer wavelengths. So on the short end of the spectrum, you see gamma rays, and then as they get longer, it becomes X-rays, ultraviolet, both far and near, then the visible spectrum, which is shown below from 350 to 800 nanometers, then the near infrared and far infrared, and finally we get into microwaves, radar, TV, FM, AM, and all other radio waves are very long wavelength. So that's our normal electromagnetic spectrum. Record answers to the questions in the student lab sheet for experiment 4 related to wavelengths. And what are the colors of the visible spectrum? First of all, we pointed out that they fall in the middle of this long, big range of the electromagnetic spectrum, and the wavelengths are between about 350 to 750 or 800 nanometers, and they range from purples through blues, turquoises, greens, yellow, orange, red, and then the deep reds. Radio waves are longer than visible waves, and higher frequency waves carry much more energy. This is because energy is proportional to the frequency. Let's move on and do experiment number 4, the continuous emission spectrum. The methodology here will be that the teacher will give out rainbow glasses to every student and a spectrum chart to each group. A fine grid pattern in the plastic lens causes the light to diffract into rainbow colors. So the grid pattern in those pieces of plastic in those glasses that you have is very, very fine and on the order of the wavelength of visible light. Let's continue on with the continuous emission spectrum. The teacher is going to turn on one lamp in the front of the class with the room lights off, and you should put on your glasses and look at the lamp. Notice all the colors are present and there are no dark spaces between each color. This is called a continuous emission spectrum. Record your observation on your lab sheet and answer the questions. So we're going to identify the emission spectra of some elements now. Each element in the periodic table emits a unique emission spectra that can be used to identify the element. And an element's unique spectrum appears in a series of lines called a line spectrum. You see one of those below. So in this experiment, some materials are needed. You need your rainbow glasses. You need a light box that the teacher will be holding up in front of the room, including some tubes that contain different gases. 3 different glass tubes containing 3 different elements. Let's call them unknowns at this time. The glass tube is going to be placed in a light box, and when the power is turned on, the electrons in the gas are excited, and they move up to higher energy levels. You could, if you've seen the picture of a Bohr atom, you know that it has a nucleus in the center and a proton, and then it has rings that surround the atoms or the elements. And what you want to do there is to realize that as the light or the power is turned on, these electrons get elevated to higher rings within that particular element. And then as they lose their power, those electrons, they transition back to the lower energy levels in the atom, and that's when visible light is emitted. And that visible light depends on how much energy change there is, and that determines the color that you see. So every element has a specific set of transitions. And those transitions show up as emission spectra. If it's different energy, it's a different color. So here is a picture of the chart that we've passed out to all of you. Your teachers passed out to all of you. And you can see on here hydrogen, helium, neon, sodium, and mercury. And what we're going to do is try to determine which gases are in the tubes that your teacher displays up at the front of the class. So your teacher is going to hold up a light box containing an element in a tube. And you're going to view the tube with your rainbow glasses with the room lights off again, so you can see clearly what colors and how many lines you're looking at. And then you're going to review your spectrum charts at your stations and choose the element that matches the emission spectrum that you see. And repeat that for the other two tubes and elements when your teacher makes a change of tubes. And then record that information in your lab sheets. The last thing will be that your teacher will need to collect your glasses and the spectrum charts from you. And if there are any other light and waves module materials at your tables and desks, please give them to the teacher. And if you didn't get to complete all your student lab sheets, you can do that now or later and hand that in to your teacher if that's what she wants you to do. All right, thank you very much. And that's the end of this module on light and waves. We appreciate you participating. Bye.